Hello, students, and welcome. Today, we're going to tackle a topic that I know can feel a little intimidating, nomenclature. But trust me, by the end of this session, you'll see it's actually quite logical and not that difficult at all.
Okay, so let's jump right in. Before we even think about any rules, let's ask a basic question. Why do we need a proper system for naming chemicals? I mean, really, why does it matter? Well, think about this for a second. How can two chemicals that look exactly the same, both are clear liquids, be so different? One is ethanol, the alcohol in drinks, which is okay in moderation. The other is methanol, a poison that can cause blindness or even death. The entire difference, the whole secret, is just one single carbon atom. And it's their names that tell us this.
You see, it's exactly to avoid this kind of dangerous life-and-death mix-up that chemists all over the world created one single universal language, a system so that a chemist in India and a chemist in America are talking about the exact same thing. And this system, this language, is what we call IUPAC nomenclature.
So what is this language really? Let's take a closer look. You shouldn't think of it as something you have to just memorize. It's much more like a logical code. Let's try to crack it together.
So here is the most important idea you need to grasp. Nomenclature is not about giving a molecule some random name. No. It's a system where the name itself is basically a set of instructions. If you understand the code, the name tells you exactly what the molecule's structure looks like.
This is a fantastic way to think about it. Using a common name like ethanol is like giving directions by saying, "Oh, it's the house near the big oak tree." It might work if you know the area, but for a stranger, it's confusing. An IUPAC name, however, is like a complete postal address. 42 Oak Lane, Block 3. It is absolutely precise. There is zero chance for confusion. And that's the whole point of it. This system exists to solve the problem of ambiguity. Before this, different places had different names for the same chemical. It was a mess. But now, one IUPAC name points to exactly one structure. You give the name pentan-2-ol to a chemist anywhere in the world, and they will all draw the very same molecule, every single time. That's the power of this system.
All right then, so how do we actually build these names? I promise you it's not some kind of magic. Just think of it like you're assembling a few building blocks in a very logical order. It's like a simple puzzle, and I'll show you the steps right now. There are really just 4 simple steps. First, we find the main backbone of the molecule. That's the longest chain of carbon atoms. Second, we find the most important part, the special part, which we call the functional group. Third, we give that special part an address, a location, by numbering the carbon chain. And finally, we just put all those pieces together to make the full name. It's that simple. Let's try it with a real example, okay? Look at this molecule. Step 1, we count the longest carbon chain. 1, 2, 3, 4, 5. 5 carbons means the root of our name is pent. Step 2, we see that there is an alcohol group attached. That gives us the ending -ol. Step 3, we have to give that alcohol group an address. We number the chain to give it the lowest possible number so it lands on carbon number 2. So we write non-2-. And step 4, just put it all together. Pentan-2-ol. See? The name is a perfect recipe for how to build the molecule.
Okay, that's the theory. But let's connect this back to the real world. Why does this precision matter so much, outside of your chemistry exam?
Let's go back to our first question. The poison is methanol, or more precisely, methan-1-ol. That meth prefix tells you it has only one carbon. The drinkable alcohol is ethanol, or ethan-1-ol. That eth prefix tells you it has 2 carbons. That tiny difference, one single carbon atom, which the name clearly tells us, is the entire reason why our bodies process them differently. One turns into toxic formaldehyde, the other into something our body can manage. It is literally a life-or-death difference written right there in the name.
And this brings me to something I see students get confused about all the time. You might see ethanol and ethan-1-ol and think they are the same. Well, ethanol is the common name, the shortcut. But ethan-1-ol is the full systematic IUPAC name. For your exams, please remember, the proper IUPAC name is the one that gives the full address, including the position numbers.
And this precision is absolutely critical in places like the pharmaceutical industry. For example, look at propan-1-ol and propan-2-ol. They have the same formula, but they are different molecules, different isomers, with different properties. Now imagine a drug company makes a mistake in the name. They might manufacture a drug with the wrong isomer, and that can mean the medicine has zero effect, or even worse, it could be harmful. See, getting the name right literally saves lives.
Okay, I know that was quite a bit of information, so before we finish, let's just do a quick recap of the most important things you should take away from this explainer.
So, 3 key things to remember. First, nomenclature is a logical code that describes a molecule's structure. It's not a random name. Second, have a simple picture in your mind. Think of it like a recipe to build a molecule, or like building blocks. And third, always remember why it matters. This code prevents real-world disasters, like confusing the poison methanol with the useful chemical ethanol.
So, for your exams, please don't just try to memorize a long list of rules. That is not the way. Instead, just focus on understanding. Remember the core idea, that the name is a code. Remember one mental picture, like the postal address. And remember one real-world example, like methanol versus ethanol. If you can hold on to these 3 things, I promise you this topic will feel much, much lighter. All the very best.